Start again.
Okay, good day everyone. You're welcome once again to MOG Economics YouTube channel. So in today's class, I'm going to be looking at the economic application of the mathematical concepts we started in the last class, in the last two classes. Um, and that is now we very quickly look at some of the areas where this concept, the ordinary differential equation, can be applied. Now, in the area of determining dynamic stability in macroeconomic models of market equilibrium. Now, dynamic stability, the word stability, I believe by now we actually understand what we mean by stability. Stability is talking about the function being stable, and I don't want to really go into that. Now, dynamic is okay, with it changes with time. It's just talking about time element, the time element. So now, this differential ODE can be used to determine the dynamic stability in macroeconomic models. So also it can be used to trace the path of macroeconomic growth, since it's a function that relates with time and so that the path of macroeconomic growth can actually use this to also yeah can easily be applied to trace the path of macroeconomic growth. You can use it in the area of elasticity. It helps economists to estimate demand function. Yes, the concept of elasticity, then how to use it to estimate demand function. So using elasticity, the ordinary differential equation also helps economists to estimate demand function, um, because now it's more or less like a growth function. And when you are introducing, I don't really want to go into this because it's beyond the class. For the sake of this class, we just have to understand that okay, another area of application is using helping economists to use elasticity to determine demand function. And also the TCTR can be gotten from this. So the integration, we introduce one of those the things we looked at or that we used frequently when dealing with the ODE was the concept of the integration. So we integrated, so we use that continuously. So the T, C, and TR are just the integrals of this. So the integral of this is this, the integral of this is this. So and the capital function from investment function is just this. This is the this is the integral of this. So applying the concept of differentiation integration rather, this can be gotten from this. Now, I want us to consider this example. So we have this is a market model. We have the quantity demand, the equation for the quantity demanded, and we have another equation for quantity supplied. Now, by equating this, when we're um, when we're looking at the concept of difference equation, yes, we looked at something like this where we equated the quantity demanded and supply function, and then we got a price. Now this is just like this is the equilibrium price. So and this is gotten by equating these two and then solving for the price, the equilibrium price. So this is the equilibrium price. Now here we're assuming that this, which is the rate of change in price with time, is a function of this. So this is excess demand. This function, this here is a measure of the excess of demand over supply. So it's just saying at equilibrium that this is a situation at equilibrium where the excess demand, this is a measure of how price changes rather with time. So at equilibrium, this is what we have, and usually at equilibrium, excess demand is zero. So the m here is a constant, is greater, is positive. This value here we say it is positive. In this case, we are assuming that okay, this is positive. So as this tends to infinity, so as we move across time, this is constant. That is, it increases because this is positive here. It shows that this increases. Now, the condition that this tends to this, that is, our price tends to the equilibrium price. So here is just showing the stability condition. So this condition for which our price would gravitate towards the equilibrium price will be a situation where which we are going to which is going to be described now. So this is, we are going to describe that condition where our price, a given price, will move towards the equilibrium price. So now here what do we have? We have this function here. We have written this. So in this case, we have replaced this, the quantity supply, quantity demanded and quantity supply with their original function here. So the quantity demanded from here is this, and the quantity supplied here is this. So now what we'll do at this point is we open the bracket, so we, and then we arrange. So here we are opening the bracket and we are arranging. We have the P, the T, so this is what we have, and here this multiplied by this, we have this. All right, so by rearranging we have, okay, all right, I want us, okay, let's expand and then we arrange. So we are expanding this again. So from here we have, now let's collect the like hand. Okay, here we have the equal sign. So we are collecting the like arms now. So we have this moving here, since they both have the P, the variable P, and then here this moves to P with this. So we have MC and we have minus MG. Then we have plus MBP minus MHP. So from here we have, let's have this before this, and very shortly we are going to see why we are doing that. All right, then this. So here we have our dp dt equal to, here m is common to these two, so we have, and here mp is common. So this changes sign, this changes this sign, then we have p, then we have p here. So bringing this term here, please, by bringing this term here, we have the p over the t plus m h minus p. Now, I want us to recall this expression from, I want us to recall the expression from last class. This, which we call the differential equation. Yeah, this is the form of our differential equation. usually it is linear. Now this equation is linear. This is considered not to be raised to any power, and these these are the constant terms we have, which can also be a function of time. Now we are assuming that this is the form of the differential equation. Now we have solved this market solution. We are in the form that it will look in a way that it will look just like the differential equation. This is the equation for the how do I put it? Okay, this is differential equation, and what we have done basically here is to solve to have our market solution to look just like this. Now if you look at this, what we have here, this looks exactly like this. Now here our v here is our m h minus b, then our z here is this, our z is m c minus g. So now we are going to apply the general formula for differential equation to solve and see if, all right, so here, sorry, this is meant to be b. All right, so now what we'll do is, at this point we are to apply the general formula for the differential equation, and the goal is to see if it is dynamically stable. We want to see if this market, now we said one of the application, the key application which we are going to be considering in this class is the to test for the dynamic stability of macroeconomic model of market equilibrium. So this basically what we are going to do in this class is to test the dynamic stability of this market model for a particular commodity in this case. So now putting it in that form, in the linear form of the differential equation, now we can easily apply that general formula. So now the general formula again is okay, let's just recall that formula, and then we'll then change some terms to reflect what we have here. So the formula from the last class is, if you remember from our last class, we have this. All right, so this is the general formula. Now we are going to rewrite this formula to suit our variables here. So what we are basically going to do here is, here instead of having y to be p, because that's our variable of interest, in this case the price. Then here our v is this in this case. So in this case our v is our a stays the same, which is our arbitrary constant. Now our z is this. Okay, I think I'll have to rub this off because I want everything to be on a single. I want us to economize this space. So now we have our v is our z is our v again. All right. So now we have our general formula looking like this, but now with a change in variables, those terms. So now what we'll do at this from here, okay, instead of, all right, what I want us to do is, I want us to still work with this formula, because working with this expression at this point will be too complex. So we are still going to work with this, but then after arriving at our result, we can then now replace our result with this that we have here. Now that we know that v is this and z is this, so let's still work with this. So what we are doing basically is, or we retain this, instead of having y t here, we are still going to have our pt. So we retain this. So we are still working with the original formula, this. So working with that original formula, we have, now we are not dealing with figures, we are working with the letters. So integrating this, assuming that this is a constant, so integrating this, we have, so here we have this. So we integrate this first, and that's vt again. So here we have this. So integrating this, we have by substitution, it means here this is our um, um, what's it called? Well, if we are differentiating this, we have, sorry, we are integrating this. So we have this, then by substitution, integration by substitution gives this. All right, and then, so this is our arbitrary constant in this case. So we have, all right. So we open the bracket with this. So opening the bracket with that, we have plus. So this, when it multiplies this automatically goes out, and I am left with this. All right. So now, for our mode, this is our result. This is our answer. So what we need to decide at this point is for our model to be consistent, because the goal of solving all of this is to determine dynamic stability of our model. Now, for this to be dynamically stable, that is, being dynamically stable will mean, okay, this pt will approach this. This is the particular integral, which is our intertemporal equilibrium. So for this to approach this, it means that as this tends to, okay, here we have, no, in this case, we have this t to be 0. That is, when this is 0, this overall expression, if we assume this to be 0, here, this overall expression from here becomes 0. Because once this is 0, this power here will be 0. This is 1. E raised to the power of 0 is 1. Then we are left with, we are left with a. This will be 1. Then we are left with a here. So our pt therefore is a. This will reduce to this. Alright, so from here, our p, now that t has been assumed to be 0, then we have p 0. Because t has been assumed to be 0, p 0 equals a plus z over v. Now, we are making this the subject. So from here we are going to make our arbitrary constant the subject. Making the arbitrary constant the subject, we have p minus this comes to the other side, and then we have this, or and say this. So we are substituting this into this and not this. So here we have a, which will have to be this, is now this. Minus vt plus. Alright, so now at this point we can now replace all this, what we have represented with v and z here, into this. So now instead of working through with this, then we work with the normal formula, the original formula, and then we'll get to this point to now replace back what we have here into this. So here we have our v, and then replacing. Now we are not just replacing this, we are also going to be making use of our equilibrium price, what we derive from our equilibrium price, which is this. So that our equilibrium price is h minus b. Okay, so this is our equilibrium price. We showed that earlier. Alright, so here we are going to be making use of this. So we are replacing this into this, and we are using this here. So this is what happens here. From here we have et. Okay, here our e0. Then here we have, okay, v, to show this, vt plus okay, what we have here is, okay, our z from here is this. Our v is this. Now, how did we get this? Someone might be wondering how we got this. The bar, p bar, something like that. Okay, here z from here is this, and then v from here is this. So here this cancels this out, and then we are left with c minus g over h minus b, which is this here. So, and that is why this, instead of writing this, we are just replacing this here. So this is representing this here. So we have b, p minus p bar, we have e t plus c minus g bar h minus b. Instead of writing this again, we just have p bar. Right. So the stability condition again is that, okay, so the result is this. So this now is the result of our differential equation for the market equilibrium. So this just is a representation, an approximation of that market condition, that solution. So here, this is the particular integral. This is our intertemporal equilibrium. And at this, we approach this. So as t tends to infinity, this overall expression here tends to 0. And then this drops out. And then this approaches this. That is, as this tends to infinity, so the price approaches the equilibrium price. Alright. So that brings us to the end of the class and the topic, ordinary differential equation. What we have been working with basically here are just symbols, letters. So we might be giving questions that involve numbers instead of figures. So you are just going to walk through the same process. So it's just the same process that we have used in this class. So all right, and then you have your answer, and that's much more simpler. See you in the next class. Bye for